So as far as I remember, we had this some problems left from the previous session. So to refresh your memory, let us start solving them. So if you remember, we were talking about mathematical induction, which was a very important and powerful tool in the hand of mathematicians when they want to prove a statement regarding the natural number, only the natural numbers. So here, for example, let me start with the examples. For any natural number n, show that so number one, if I remember correctly, one of these are some of the problems that I assigned for you last time. So we have 1 to power 2 plus 3 to power 2 plus 5 to power 2 up to plus 2n minus 1 to power 2. We are supposed to show that this is equal to 4n cubed minus n divided by 3. Yes? Am I right? This is one of the problems, yes?
Yes.
Okay, so we want to show this. So this, we call it Pn. So this is our Pn. I don't need to rewrite it again. The first thing that I need to check is P1, yes? So let me change the color. So you calculate P1. So what is the meaning of P1? So this means that you will start with n equal to 1. This is the general formula for you. And then you plug n equal to 1 here. This gives you 1 to the 2, and that's exactly the first term. So it means that when you plug n equal to 1 on the left-hand side, there is only one term involved, and that is this expression. So 1 to power 2. And I need to ask myself, is this correct if I put n equal to 1 on the other side? So it means that 4 times 1 to the 3 minus 1 divided by 3. Yes? But I think it's very easy to check. 1 to power 3 is 1 times 4 is 4 minus 1 is 3. 3 divided by 3 is 1, and 1 to power 2 is also 1. So yes, this is true. Now, if you remember, we are supposed to assume that if k is a natural number, then pk is assumed to be true. Technically, writing pk is very simple. You just replace n with k everywhere. So then it becomes 1 to power 2 plus 3 to power 2 plus 5 to power 2 up to 2k minus 1 to power 2 is equal to 4k to the 3 minus k divided by 3. So this is assumed to be true. Yes. And now we want to show that based on the truth of this that we take for granted, we want to show that pk plus 1 is also true. Yes. So here we have this. But in order to write pk plus 1, it means that you are supposed to replace k with k plus 1 everywhere. So this means that this is 1 to power 2 plus 3 to power 2 plus 5 to power 2. And then you continue. You need to replace k with k plus 1. It means that you have to write two brackets around it, k plus 1 minus 1. But if you simplify that, it becomes 2k plus 2, and then you have a minus 1. So this becomes 2k plus 1 at the end. So if I replace k with k plus 1, this expression becomes 2k plus 1 to the 2. Yes. So this becomes 2k plus 1 to the 2. And of course, you have some experience now that if you want to prove these things, it is always instructive to write the previous step. So the previous step is 2k minus 1, of course, to power 2. And then here on the right-hand side, you replace k with k plus 1 everywhere. So this becomes 4k plus 1 to the 3. But if you write like this is wrong, yes? So you need to put a pair of brackets around that. So instead of this k, I replace k plus 1. And then I have divided by 3. So that is the point that I want to show. Okay, so sometimes it would be better to simplify this expression a little bit, but let us not to do that for the time. Yeah, I think in this case it would be much simpler if I simplify, because otherwise it's not that clear what to do. Okay, let us start as we usually do, and then if there are some problems, we try to solve it when on the fly. Okay, so here I want to prove that the left-hand side is equal to the right-hand side. So this is my question mark. This one is assumed to be true. Based on this and my previous math knowledge, I am supposed to show that the left-hand side of this is equal to the right-hand side. Okay, so I start writing the left-hand side. So in the left-hand side, you see from here up to here, and then you have an extra term. But based on the assumption of the induction, I know that the sum of the first k terms is actually this one. Yeah, it's exactly this one. So instead of this expression here, I put this expression, and then I continue with one term extra, yes? So the left-hand side becomes 4k to the 3 minus k divided by 3, and then I have plus 2k plus 1 to the 2, yes? Okay, the point is to simplify this, do some simple algebra, and try to show that this one is equal to this one, which is the right-hand side. So the first thing that motivates me is that when I look on the right-hand side, that I see that I have only one fraction. So what I do is I take the common denominator here. So the common denominator clearly is 3. So I will write 3 here, and then I have 4k to the 3 minus k, and then I have plus 3 times 2k plus 1 to the power of 2. Okay, so what I need to do, I want to prove that this expression is equal to this expression. So that is, of course, it is not that hard to do it directly and then continue until I reach to this side. But this is not a necessity, even though I myself prefer to start from this one and reach to that one. But if that's going to be hard, what you can do, you can simplify this expression as much as possible. You can also simplify this expression as much as possible, and then they compare the final results. So if the simplified version of this is equal to the simplified version of that, it means that also this one is equal to that one, yes? That's up to you. Usually, sometimes it's easier. Okay, so what I do here now, I concentrate on this expression, 4k3 minus k plus 3 times 2k plus 1 to power 2, yes? And I will try to expand and simplify this as much as possible. So it becomes 4k to the 3 minus k, and then I have plus, I raise it to power 2, and then multiply it by 3. So let us do it in one go. Okay, so this one to power 2, the first one to the 2 is 4k squared. But I multiply it by 3, it becomes 12k squared. And then I have 2 times this one, that one, it becomes 4k, 2 times the first one times the second one. Then I have an extra 3 here that I will multiply it here, it becomes 12k. So the next one is 12k. And finally, the last one to the 2 is 1. And then I have another 3 which comes and multiplied it. So it becomes 3. So this becomes plus 3. And then the denominator is 3. If I want to simplify it a little bit more, 4k to the 3 is alone. And then 12k squared is also alone. But minus k here and 12k here, it becomes 11k, and then I have plus 3 at the end divided by 3. So what I'm saying is that the simplified version of this expression is this. Okay. Of course, it's not hard to see that this expression is equal to this expression, but let us simplify the other one as well. So 4k plus 1 to the 3 minus k plus 1, then divided by 3. Yes? Okay, if I want to simplify this expression, there is another formula. Usually it's in the formula sheet, but nobody cares about that usually, and that is this formula. If I have a plus b to power 3, this becomes the first one to the 3 plus 3 times the first one to the 2 times the second one plus 3 times the first one times the second one to the 2, and finally the second one to the 2. Okay, so I use that one. I use this formula, this is an algebraic identity, to expand this expression. K is playing the role of A, and 1 is playing the role of this B, yes? So then what happens? So it becomes 4K. It becomes 4. K plus 1 to the 3 becomes the first one to the 3 plus 3 times the first one to the 2 multiplied by the second one, but second one is 1, so no points about that. Then I will have 3 times the first one times the second one to the 2. Second one to the 2 is just simply 1, so no problem here. And then the second one to the 3 is 1. And then I have minus, I open the pair of brackets, it becomes minus k minus 1. Yes, and then I expand this, it becomes 4k to the 3 plus 12k squared plus 12k plus 4 minus k minus 1 divided by 3. And then one more step, I have 4k to the 3 alone, I have 12k squared alone, and then you see that 12k minus k is again 11k. And then finally, I have 4 minus 1 is positive 3, and then I have this divided by 3. Okay, and then if you see, the simplified version of this is this one. The simplified version of this is also the same expression. You see, you compare these two together. If the simplified versions of these two are equal, so it means that they themselves are also equal. And it means that in this way, we were able to show that pk plus 1 is also true. And then by mathematical induction, this is true for all possible choices of n. So that's also one possibility. If you see that sometimes it becomes hard to go directly from the left-hand side to the right-hand side, you can use the assumption of the induction and write and simplify that, and then go to what you want to prove on the right-hand side, simplify that, and then compare the simplified version of those two expressions. Okay, there was one more, I think, at least. Let me solve that one as well. So, any questions so far?
No.
Okay, good. So if I remember, this was also one of the questions that I mentioned. 1 times 3 plus 2 times 3 to the power of 2 plus 3 times 3 to power 3, and then you continue until n times 3 to power n is supposed to be equal to 3 over 4, and then you have 2n minus 1 times 3 to the n plus 1. Okay, we are supposed to use mathematical induction to prove this formula. Okay, so again, let me not repeat this. This is your statement about P. So the first thing that you do is to check P1. So what is P1? So P1 means that you need to replace n with 1. So when you replace n with 1, you get the first term. So it means that this is end. You need to stop there. So P1, the left-hand side is 1 times 3. You need to ask yourself, is this equal to the right-hand side when n is replaced by 1? So 2 times 1 minus 1, 3 to power 1 plus 1. Okay, so you need to write it in this way in the exam. So it means that you are showing that you are replacing n with 1. And then you want to see that if this is true or not. But let us simplify. The left-hand side, 1 times 3 is nothing except 3. But let us calculate this. 2 times 1 minus 1 is 1, times 3 is 3, plus 1 is 4. So the whole bracket is 4. So it becomes 3 over 4 multiplied by a 4. 3/4 times 4 is just 3. So this implies that this is 3 equal to 3, which is a true statement. Yes? And then what I do, I consider that this is true for k, for a natural number k. 1 times 3 plus 2 times 3 to power 2. This is very easy to write. You just replace n with k everywhere. You don't need to be careful at all. So k times 3 to power k, the right-hand side is 3/4 of this expression 2k minus 1, 3 to power k plus 1. Yes. And then I am supposed to write k plus 1. This assumed to be true. This is the assumption. Okay, and then what I want to show is that if I continue this process up to the k plus first term, up to k plus first step, yes. So of course I need to replace k with k plus 1. So this becomes k plus 1 in pair of brackets times 3 to power k plus 1. Here in the exponent I don't need to put pair of brackets. On the right hand side I have 3 over 4. The same story, yes. So this k should be replaced by k plus 1, so it becomes 2k plus 1 minus 1. It becomes 2k plus 2 minus 1, so it becomes 2k plus 1. Yes. So this becomes 2k plus 1, and then instead of 3 to power k, I have 3 to power k plus 1, and then I have plus 1 at the end. So this has to be proven. But of course, you have enough experience that when in these problems you write the k plus first step, it's always better to write the previous step, which is k times 3 to power k. Okay. Now I start from the left-hand side of this question mark. Yes, this is my question mark. I want to show the left-hand side is equal to the right-hand side. I start from the left-hand side. The whole power of induction actually lies on this fact that you can replace this with what you assume to be true, this expression. So instead of this part on the left-hand side, I put this one, which I have assumed to be the case. So then it becomes 3 over 4, 2k minus 1 times 3 to power k, and then I have plus 1. And then you see what I wrote here was what I replaced for this one. There is an extra term left, so I need to add that one as well. So it becomes k plus 1 times 3 to power k plus 1. Okay, I need to simplify this a little bit. Let us continue so that we can reach to the right-hand side. So by having an I on the right-hand side, you see that I have an overall factor of 3 over 4. But here I do not have an overall factor of 3 over 4. This factor of 3 over 4 is only for the first part. So this might motivate me to factor 3 over 4 out from all this expression, okay? That is what I want you to learn. So what happens is that I will have this expression, yes, so let me write it, 2k minus 1, 3 to power k plus 1. But of course you see that there is no 3 over 4 here. I have taken this out, so it means to compensate for that, I need to write 4 over 3 times k plus 1 3 to power k plus 1. Yes, so let me explain it again. So what is the meaning of factorization? Factorization is valid if you multiply this back and you get the same answer. So let us check. If I multiply this number here, I will get exactly this term. If I multiply this 3 over 4 here, this 3 over 4 that I multiply and that 4 over 3 that I wrote it intentionally there will cancel each other to 1. And then what is left for me is just this expression. And that is exactly what you see here. So this validates what I have done, yes? This 3 over 4 is taken care of. Why this is good? Because now if I have an I on the right-hand side, I see that this 3 over 4, which I need on the right-hand side, actually appeared. And then it means that I need to focus on simplifying this expression and show that this expression is indeed equal to this one inside it, okay? And that's also good because now you see that there is a 3 here, and then I have 3 to power k plus 1. These two can be simplified. 3 to power k plus 1 divided by that 3. If you remember, I need to subtract the exponents. The exponent here is 1, so it becomes k plus 1 minus 1, and it becomes 3 to power k. So it means that instead of this one and this one, I can simply write 3 to power k. So let us do that. So this becomes 3 over 4. Then I have 2k minus 1, 3 to power k plus 1. And then I will have 4 times k plus 1, 3 to power k. But now again, let us see what I need on the right-hand side. I need the positive 1, good, I have it here, so no worries about that. But you see that I have an expression multiplied by a power of 3. But here I have 2 powers of 3. So this motivates me, might be I should be able to factor this 3 to the power of k out here. I mean, it might be helpful. So let me see if it is indeed the case. So I take 3 to power k out. I pulled this 3 to power k out here. So what is left from the first one is 2k minus 1. So I would write 2k minus 1. Then from this one, I pulled 3 to power k out here. So what is left for me is plus 4 times k plus 1, which I write it here. Yes. And then you see I have a plus 1 here, so I write it here, and then I close the pair of brackets. Hopefully everything is in order. Now you see, if you compare this one with this one, they are similar, but not 100% the same now. Let me simplify that expression. Yeah, continue simplification. So we can do this here. So this is 2k minus 1, and then I multiply 4 inside, it becomes 4k, and I multiply 4 by 1, it becomes positive 4. But look, 4k and 2k becomes 6k, minus 1 and positive 4 becomes positive 3. And then I can factor a 3 out, so it becomes 2k plus 1 multiplied by 3. So this expression is exactly equal to this expression here. Okay, so remember, I will write 2k plus 1 times 3 instead of that expression. So it becomes 2k plus 1, yes, times 3. So what I wrote here was the answer to this part, but I have another factor of 3 to power k, so it becomes 3 to power k. Then I have a 1 at the end. But everyone knows that there is a better name for 3 times 3 over k. The power is here. The exponent is 1, the exponent is k. I need to add the exponents. So this becomes 3 over 4, 2k plus 1, 3 to power k plus 1 plus 1. And that's exactly the right-hand side. Yes. So this is also one of the problems that I gave you last time. There is only one problem left, so let me do that one as well. So number 3. Any questions so far? No? Okay, so the other one, if I remember, is this one. So I have it here. I think this was the one that we are supposed to solve. So that's a product of 3 terms in the denominator, and then you have 6, 2 times 3 times 4, and then 7 over 3 times 4 times 5, and then this continues so that we reach to the last term, n plus 4, n times n plus 1, n plus 2. And on the right hand side, I will have n, 3n plus 7 divided by 2 times n plus 1 times n plus 2. So we are supposed to prove this one. Okay, so what I do, I call this one Pn again. This is what I want to prove. So the first thing that I do is to calculate it, to check the validity of P1. Is it true or false? Okay, so what is P1? If you put 1 here, this becomes 5. The denominator becomes 1 times 2 times 3. And that's exactly the first term. Okay, so it means that when I give n equal to 1, only the first term on the left-hand side will be involved. Yes? What happens on the right-hand side? So there's a question mark. It becomes 1 times 3 times 1 plus 7 divided by 2 times 1 plus 1, 1 plus 2. But is this true or false? The left-hand side is 5 over 6, so this is completely equivalent to 5 over 6, the left-hand side. The right-hand side, the numerator, what is the numerator? The numerator is 10 times 1, which is 10. The denominator is, this is 2, this is 3, so 2 times 2, 4 times 3 is 12. Is this true? Yes. So this is a true statement. Because 5 over 6 is another name for 10 over 12 if I simplify this by 2 and simplify this by 2. So the first state, the base of the induction, this is called the base, it's true. Now I assume that P for a natural number K is also a true statement. This part is easy, so let me just copy and paste quickly everything, but I only need to replace, let me write it better. So, but I just replace n with k everywhere. 2 times 3 times 4, and then I have 7 over 3 times 4 times 5. It continues until I reach to k. Let me write a little bit further because you know why, because I need to add the previous, oh, sorry, no, this is not that step, sorry. I just replace n with k. K plus 1, k plus 2. And on the right hand side, I will have this. K times 3k plus 7, and then I have 2k plus 1, k plus 2. For pk plus 1, you need to be a little bit more careful. So this means that I have 5 divided by 1 times 2 times 3 plus 6 divided by 2 times 3 times 4, 7, 3 times 4 times 5, and then I continue until the k plus first step. So it means that wherever I see k, I replace it with k plus 1. It is very easy to see that the numerator becomes k plus 5, and the denominator becomes what? K plus 1. The next one becomes k plus 2. The next one becomes k plus 3. And on the right hand side, you shouldn't make mistakes. Hopefully I can use this space to finish it. So this becomes 2. The denominator becomes k plus 2, and then k plus 3. The numerator becomes k plus 1, but what happens for the next one? I replace this k with k plus 1. Yes, and then I have a 7 at the end. So this becomes 3k plus 3 plus 7. It becomes 3k plus 10. So that is what I need to put here. So it becomes 3k plus 10. And then of course I told you that usually it's always better to write the previous step, but the previous step is just this one. So I just write k plus 4 divided by k plus 1, k plus 2. Okay, so this is again assumed to be true. But this is what we want to show. Again, I start from the left-hand side of what I want to show, and then you have enough experience by now. You know that this hard part is actually can be replaced, but what I am assuming about it using the assumption. So everything here, the whole expression here will be replaced by this simpler expression, okay? So this becomes equal to k times 3k plus 7, and then you have 2 times k plus 1 times k plus 2, and then you add this term to it, yes? K plus 5 divided by k plus 1, k plus 2, k plus 3. Okay, if I have an eye on what I want to prove, I see that I have only one fraction on the right-hand side. So this will motivate me to take the common denominator between these two expressions. And the common denominator is actually what is the least common multiple. So it means that I need to write an expression for the denominator which is divisible by this, also divisible by this, and I don't need to write more than necessary. So it means that I need to write 2, k plus 1, k plus 2, k plus 1 and k plus 2. I don't need to write an extra because I have already taken care of that. I need to write k plus 3. So it is clear that the common denominator is 2 times k plus 1, k plus 2, and finally k plus 3. Then I would say that this, if I divide it in my head by this one and that one and that one are gone, k plus 3 is left. I multiply k plus 3 in the numerator here. So this becomes k times 3k plus 7 multiplied by k plus 3. Then I have a positive plus sign here, and then I compare this with this one. If I divide these two, then only 2 is left because these are actually gone. So this 2 is left, I multiply 2 in this numerator. So it becomes 2k plus 5. Of course, if you have another look on the other side, so you see that it's better not to multiply this because this and this and this are actually here, but we have only one extra term which we don't like. And then if you have enough experience, you probably know that if I simplify this expression, I can probably factorize something that will cancel. But factorization of these are not that easy because this is a third degree polynomial here. Let us see how it goes, okay? So what I'm saying is that I will keep the denominator untouched. So this is 2k plus 1, k plus 2, k plus 3. And then what can I do here? I start multiplying these. So I have to multiply k here. And then when I found the answer, I multiply the whole answer here. Okay. Okay, so let me just do it here. So if I multiply this one, it becomes 3k squared plus 7k. Yes? So remember, this, what I have written here is the answer to this one, and then I multiply this here as well. Okay, so I'm just writing that one. So 3k squared by k, it becomes 3k cubed, and 3k squared by 3, it becomes 9k squared. Then 7k by k becomes 7k squared, and 7k by 3, it becomes 21k. And then here I multiply these 2 inside as well, so it becomes 2k plus 10. So here what I do, I just write it 3k to the power of 3 plus 9 and 7 becomes 16k squared, and then 21 and 2 becomes 23k, and then I have a 10 at the end, and then you see what's my problem here. So this becomes 2k plus 1, k plus 2, k plus 3. Okay, but of course it is not still equal to the right hand side. If I want to reach to the right hand side, it's clear that I have to factorize this expression, and this is not easy. On my YouTube channel, I have 4 complete lectures about how to factorize polynomials for different ones. And then I think the last videos are related to factorizing polynomials using a method called long division method. Okay. Even though you might not know about those things, but it is not impossible to solve this problem, because if you trust your calculations so far, you know, so what I'm trying to say is that I am not going to teach you how to factorize this, because that's whole a new lesson, which is not necessary for this. But it is not impossible to understand what is the factorized form of this expression if, of course, you have been careful and have done the calculations very carefully so far. So you see, this is supposed to be equal to this expression. Okay, so 2 and 2 are the same, k plus 2 and k plus 2, k plus 3 and k plus 3. Okay, so it means that I need to get rid of this k plus 1. Okay, but if this has only one factor of k plus 1, that factor and this factor are totally gone. For the denominator, that's quite okay, but there is no factor of k plus 1 left anymore, but I need another factor of k plus 1 here. So if I have done everything correctly, there should be 2 factors of k plus 1 here. So it means that it should be k plus 1 to power 2, and then multiplied by 3k plus 10, yes? So this is my rough guess. You see, if this expression in the numerator, so if this expression is equal to k plus 1 to the 2 times 3k plus 10, if this is true, then I am done. Why? Because when I put this instead of this question mark, one of these k plus 1s and one of these k plus 1s here are cancelled. The denominator is completely fixed now, and 1k plus 1 will be remained in the denominator, which is necessary here. And there is a 3k plus 10 left, which I need this. So this is my rough guess. My rough guess is that the question mark should be k plus 1 to power 2, 3k plus 10, yes? So if I were you at this stage, I would say that, okay, I would say that now, I'm just a little bit cheating, yes? Now I show that 3k to the power of 3 plus 16k squared plus 23k plus 10 is equal to k plus 1 to power 2, 3k plus 10. Okay, but now instead of factorizing it, which is a hard process, and show this is equal to this, I start from the right-hand side and reach to the left-hand side. So still, what I say is that, okay, now the right-hand side is equal to, I expand this to power 2, it becomes k squared, 2 times the first one times the second one, and the second one to power 2, multiplied by 3k plus 10. Expansion is not hard, I just multiply, but factorization is a whole new lesson itself. Okay, k squared times 3k, it becomes 3k cubed, and then I have 10k squared. Then I go to the next term, it becomes 6k squared, then I have 20k. then I have 3k, and finally I will have 10. And then what I do, 3k cubed is alone, but here I have this one and that one, which is 16k squared. And then this one and this one is 23k. And then the last one is 10, and that's exactly the left-hand side. Okay, therefore, the left-hand side is equal to, so you see, I reached to this point, I started from the left-hand side, I calculated all the way around, I reached to here. Then I showed that this expression itself is equal to this. So I would say, therefore, the left-hand side is k plus 1 to power 2, 3k plus 10, and then divided by 2, k plus 1, k plus 2, k plus 3, and then you see that this k plus 1 and one of these are gone. So what is left for me in the numerator is just one factor of k plus 1, one factor 3k plus 10, and three factors in the denominator, 2, k plus 2, and k plus 3. And then this is exactly the right-hand side. Yes? So somehow you need to learn how to sometimes cheat if you actually reach to a hard problem. Any questions?
Yes, Mr. Wawak.
Yes?
Couldn't you simply, instead of doing all of that,
Yes?
just take the right-hand side and multiply the denominator and denominator by k plus 1? I mean, I guess that would be the same thing, maybe.
Yeah, that would be the same thing usually. Yeah. It is not simpler than this, but this is more a logical way of doing that, because when you equate them and multiply, it means that you already take it for granted that they are equal.
Okay.
Yeah. But of course, that's also true if the arrows, if your conclusions are double-sided, reversible. Yes, we talked about this in mathematics specialization. If you want to show equality, instead of showing that equality, you start simplifying that equality, and you reach to something which is trivial. This is valid only if all the operations that you have done are reversible. Yes, of course, in that case, that's also true. So you equate them, and you start simplifying that equation, that equality, to come to a true equality, but you need to be careful to write double arrows, yes? Double-sided arrows. Okay, now, so this is more or less, now you have enough experience, but there are some details that I want to talk about mathematical induction today. So one thing is that, so I don't want to expose what I want to say. First, I want to test you, okay? So these are simple ones. So the algebra are very simple, and I just want to wait a little bit for you. So let me write examples. So these examples that I am just mentioning right now are much, much simpler than these examples, but the points lie somewhere else, okay? So example, so let me see, how do you think about this problem? So example, I want to wait a little bit for you. So for any natural number, by mathematical induction, of course. So let me write this sentence in this way. Using induction, so it means that even if you know another way to solve it, don't do that. Using induction on n, show that for any natural number n, we have this. We have 1 plus 2 plus 3 plus up to plus n plus 2 is equal to n squared plus 5n plus 6 divided by 2. Okay, I just want to wait a little bit for you, 2 or 3 minutes, because I don't want you to fully solve this problem. I'm sure that you know that. But I want to see that, do you catch the problem, catch the points of this problem here? And whenever you are ready, you can talk to me, and then I...
P1 is false, I think.
Okay, so yes, let us discuss about it. Let us discuss about it. So if you say P1 is false, so it means that I am not allowed to ask you to prove this, yes, in the first place, because when I see prove it, it means that this is valid for all possible choices of n. So what do you think now?
Maybe we have to shift it, or add in like, so an
No, I mean
exception,
that, do you think that P1 is false or true? So that's a very good question. So let me, this is your Pn. So here, your Pn is this. So let me make it clear by writing a different color. So this is a very important point. So let me put a star here. Okay, so Pn is this expression, 1 plus 2 plus 3 up to plus n plus 2 is equal to n squared plus 5n plus 6 divided by 2. My point is that, you know, if you want to prove something, first of all, I have mentioned that show this is true. So indeed, this is true. But the first thing that you need to do using mathematical induction is check the truth of P1. So now my question for you is this. Is P1 a true statement or a false statement? If that's a false statement, so this means that I don't have the right to ask you to prove it in the first place, because it doesn't work for one. Even if it works for everything, it doesn't work for one, so it's not something that I can rely on.
It's false.
Okay, so you are saying that P1 is false, so it means that this question is false, yes? But I would say no. This identity that I have written here is completely correct.
Is it that if it's P1, we should only like disregard? No.
No, so this is what I want to say, because based on experience, I know that
okay,
usually
so
take P1 for granted. You take the first one, and they say that, okay, the first one is equal to P equal to 1, but this is not the case. You need to read it in a correct way.
Can we,
okay?
it's like Fibonacci, where the first two ones are like defined by a separate equation. So we have to try P.
No. This equation is valid for all choices of n. Your interpretation is wrong. Let me correct it for you. Any other opinions?
If the sequence starts at n equals to -2, will it work then?
No, this is the, you see, there is no sequence. You are more or less right, but this is an expression. This claims that the left-hand side is equal to the right-hand side, and if you trust me on that, I would say this equality is true. But when you check P1, you check it in this way. You say 1 is equal to 1 squared plus 5 times 1 plus 6 divided by 2. Then you would say this is equivalent. The left-hand side is 1. The right-hand side, 6 plus 5, 11 plus 1 is what? 12 divided by 2 is 6. So you say 1 is equal to 6 is false. This is the way that these examples so far somehow motivate you to do it in this way. And the reason that I always talk about how to think P1, sometimes you say that Babak is talking too much, why he's always explaining about P1. This is the reason. So P1, you need to interpret it. This statement doesn't tell you take the first one. It tells to you that you give me an n, okay? I add 2 to it, I start from 1 until I reach to n plus 2. Then I stop. Is that understandable? So if I want to write the left-hand side, I give you an n, and I ask you to write this for me. You start from 1, go 1 at a step, up to reaching to n plus 2. Okay, then you stop. This is the way that you need to interpret this sequence, this sum. Okay, now assume that I give you n equal to 1. It means that I need to start from 1 and start adding numbers after the other until I reach to this level n plus 2. But n plus 2 would be 3 in this case, so it means that if you want to check P1, P1 is this statement. So this is P1. And now tell me, is P1 true or false?
It's true.
It's true.
It's true. So it's very, very important. Of course, most of the examples last session and this session, you could be careless and just take the first term. Yes, here we also took the first term, you see. But the interpretation is very, very important. If you want to prove this, if you write 1 equal to whatever, you get a false statement, then you get confused. But P1 sometimes is tricky to write. P1 is this statement, and then you need to ask this question. So let me repeat this one again. So you need to interpret this. This sum on the left always starts from 1 and will be added to the next number, will be added to the next number until you reach to the level n plus 2. If n is equal to 1, the level n plus 2 is 1 plus 2 is 3. So it means that I start from 1, I continue until I reach to the right level. The right level is 3 in this case. So it means that this is the correct way of interpreting P1, and this is 6 on the left-hand side. And if you remember, I just calculated the right-hand side, that's also 6. Then I would say that this is true. It's a very, very important point to remember.
So, Baba,
No questions? Yes?
what is the difference between this one and the ones you did, like this session, the last session? How do we know that we need to think that way when we're doing
I
this?
just explain all these things that you understand that one. In the previous one, for example, here, if I put n equal to 1 here, it becomes 1 to power 2. 1 to power 2 is exactly the first term. Yes? So this shows that if I start from here, I continue up to this point, then I am so if I put n, let me just, if I don't want you to memorize that, but I can just give you how to understand that. You put n equal to 1 in the last term. If this is the first one, you just keep it the first one. If it turns out to be the second one, you need to write from the first one to the second one. If it turns out to be the third one, you need to write first, second, and the third one. Yes? So this is a rule of thumb. I don't want you to memorize that because this is not mathematics, but at the end of the day, this trick that I am teaching you works for all of them. For example, here, if I take n equal to 1, what will happen? This becomes 5, this becomes 1, the next one becomes 2, the next one becomes 3. And if you look, this is exactly the first term. So P1 only includes one term from the left-hand side. But now look here. If I put n equal to 1, what happens? It becomes 3. 3 is not the first term, is not the second term, is the third term. So then you need to keep all of them from the first term up to that number. This is the rule of thumb. Yes? Is that understandable?
Yes, it's better. Yes.
So that's a very simple trick, but I don't like it because this is just something like Okay, don't understand, just do this. Okay, but if you want to understand, you need to interpret this in the right way, so that's the case. But this method will always work. You put n equal to 1 in the last term, and then it will produce you one of them. If this is the first one, keep only the first one. If this is the second one, keep the first one and the second one. If this is the third one, keep the first, second, and the third one, and so on, okay? Okay, so I don't want to continue this problem. So this problem, because this is very, very simple now for you, I solved harder problems than this, then you can continue. You can assume that this is valid for k, and then you should prove that this is also valid for k plus 1, which I leave it as an exercise because I have another problem to say. Okay, here, the next example, so let me write here. You continue yourself, yes? Yes. Okay, now let me give you another one, which is also very important. You might have this feeling checking P1 is irrelevant, yes, because this is going to be true. So why should I bother and check P1 all the time? First of all, I hope that at this level you understand it, you feel it, that this is indeed necessary, yes? Because in the going from assumption to the one that we want to prove, what we do when we go from this step to this step, we show that if a step k is true, I show that the next step is true. But if I ask you based on this, can I conclude that P1 is true, P2 is true? You would say no. If you tell me P1 is true, based on this step, I can say P2 is true, but there is no guarantee that P1 is true. If you say P10 is true, using this argument, I can say, yes, okay. If you say that P10 is true, I can show that P11 is also true. So it means that if you do not look at the base of the induction, there is no starting point. So it is very easy to see logically that you need to start from somewhere, show that this is a valid and firm step that I can put my feet on. And then I can show that if I am on a step, then I can go to the next one, okay? If I'm on a stair, I can go to the next one. Let me emphasize this by an example. Actually, it's a non-example, okay? So let me write it here, example. I don't know how to say it. Show that, so because this is not going to be correct, show that 1 plus 2 plus 3 up to n is equal to n squared plus n plus 2 divided by 2. Of course, you clearly know that this is a wrong formula, yes, because you know hopefully the correct formula. The correct formula is this. Do you remember? This was the correct formula, and if I multiply it, it's n squared plus n, divided by 2. N squared plus n divided by 2 is not n squared plus n plus 2 divided by 2. So if this one is right, definitely this one is wrong. But let me be careless and do not check P1 explicitly. You see, I want to emphasize that checking P1 is really important. It's not just for decoration there, okay? So let me try and be careless. Now assume that I am a careless student. I don't care about P1. I would say that, okay, P1 is always true, so why should I bother to check that? So then I would say that, okay, PK is true. What is PK? It's 1 plus 2 plus 3 up to K is equal to K squared plus K plus 2 divided by 2. Yes, and this I assumed to be true. So you see, I am following exactly everything except that I didn't check P1 individually. Assumed to be true. Okay, now I show that PK plus 1 is true. 1 plus 2 plus 3 plus k plus 1. By experience, you know it's better to write the previous one. And I replace k with k plus 1 everywhere. Yes? Okay, my point is again as before, so let me just do this fast because you already know. I start from the left-hand side. Left-hand side is equal to. Instead of this part, I put this one that I assume to be true. So it becomes k squared plus k plus 2 divided by 2 plus the next term is k plus 1. Yes, because I replace this with this, k plus 1 is left. So let me write k plus 1. And then let us simplify this by taking a common denominator 2. The first one becomes k squared plus k plus 2. I multiply 2 by that, it becomes 2k plus 4, yes? And now what happens, I can write it in this form. It's k squared plus 2k. Instead of 4, I write 1 here. And then I would write k plus 1 and then plus 2. I will explain it right now. Divided by 2. Okay, so you see, k squared is k squared. 2k is 2k. Okay, and then k is k. And then I have 1, 1, and 2, which is 4. So what I have written here is completely valid. But you immediately realize that this is k plus 1 to power 2. It becomes k plus 1 to power 2 plus k plus 1 plus 2 divided by 2. And that is exactly the right-hand side. So you see, if you don't care about P1 using mathematical
Baba?
induction, yes?
I have a quick question. Why do you
Yeah.
why did you wrote k plus 2 instead of k plus 1?
I wanted to reach to the right-hand side. In the right-hand side, I see k plus 1, I have it. I can write k plus 2, but I just chose to, because of my goal is to reach to the right-hand side, yes?
No, not there. K squared plus k2, k plus k2 divided by 2 plus k plus 2. There.
Here? Here?
No, before that.
Here? Here?
Yes. Why did you write k plus 2?
You are right. Why I did that, I don't know. Thank you very much.
Yes.
Yeah, so you need, I told you, you need to tell me immediately. Okay, good. Thank you very much. So here, let me, this is, yes, this is k plus 1. You were right. So this is k plus 1. So that's k plus 1. Let me double check everything. So instead of this, I put that one, that's correct. But after that, it is k plus 1. That's also correct. But when I multiply it by 2, it becomes 2k, not 4. It becomes k plus 2, yes? Hopefully it will not affect anything. So this becomes 2. Yes, but everything is now correct. Yes, I don't know. I was living in another world probably. Yes, here. You see, k squared plus k plus 2 is this expression. That's right. And 2 multiplied by k is 2k. And then 2 multiplied by 1 is 2. So that's right. And then k squared, 2k, 2k, k and k, and 1 plus 1 plus 2 is 4, 2 plus 2 is also 4. Now is that okay?
Yep.
Yeah, okay. But anyway, it is the right-hand side. So you see that everything that I have done here is exactly according to what I told you before. In the previous examples, we did the same thing. We assumed that pk is true, and then we showed that pk plus 1 is also true. So it means that it is very important. The people who have just mathematics specialization with me, this is a logic, you see. This is a wrong statement, but if you say this is true, I can also show to you that this is also true. Just a little bit for the people who have math specialization, this is a false statement. So from the false statement implying a false statement, we learn that this is true. So this is completely correct. Now forget about those people. Now in Math 5, you see I started from something which I know it is wrong, and I showed that if you say to me this is true, I am able to show you that this one is also true. The only reason that this statement is not true, so you cannot say that, okay, mathematical induction is proving something wrong. No, because you are not respecting the entirety of mathematical induction. You think that this is the important part. Yes, the important part or the tedious part is working, but you still need to check P1. If you don't check P1, you are able to prove wrong statements. Yes, but now assume that now I am a careful student. I know that, let me write a different color. I know that I have to check P1 first. But when I check P1, the left-hand side becomes 1. The right-hand side becomes 1 to the 2 plus 1 plus 2 divided by 2, which is false. So if I am a careful student, I save time for myself, yes. When I check P1 and it doesn't work, I even don't care to go to the other part of the induction. So what I'm trying to say, this is a very simple and nice example to show that this step works even if you are proving something wrong. Because it tells you that if you tell me this is correct, I show that the next one is also correct. That is not my responsibility that this is correct or not. This is why I don't know if I can transfer my feeling to you, but that's the case. So this is not a fantasy. You have to check P1. If P1 is false, just stop there. Yes, your teacher or the book has some misprints or something. You need to fix it first. So hopefully you understand. Do you understand what's going on?
Yes.
Okay. So now there are many parts of the induction left. We have a little bit of time. What do you remember? I told you the weakness of induction. What was the weakness of induction?
We have to have a statement. We can't.
Yeah, exactly. Yes, in principle, if you go back here, for example, if I give you this and I ask you to compute a closed formula means a formula without these dots. For this one, and without giving you this, you need to be very creative, or you need to know how to deal with these series to be able to find the formula, okay? But sometimes if the pattern is not that complicated, I don't know how many of us would be able to guess this formula if we want to work with different numbers here. But usually if the pattern is not that complicated, you can guess the pattern. Guessing the pattern is not a rigorous mathematical proof. But if you prove your guess using mathematical induction, that is a mathematically valid proof. Yes. So for example, let me just give you a motivation. I give you a simple example to you. I'm sure that you can guess that one. So example. So I don't know how to say. So let me write determine a closed formula for the following series. This is a very simple one to guess because I just want to give you the essence of what do I mean. So 1 divided by 1 times 2 plus 1 divided by 2 times 3 plus 1 divided by 3 times 4, and then you continue until 1 divided by n times n plus 1. So you see, I have mentioned determine a closed formula. I haven't asked guess a closed formula. But the first part might be, you might be creative. There is a very nice way to calculate this sum, but forget about that. The lesson is about induction, so let us focus on that. What you can do, you can try to play around with this a little bit by choosing different values for n, and then try to see what the pattern is. Based on that pattern, you can guess a closed formula and then say that, okay, this is the formula that I propose. Then you will have your statement in its entirety, the left-hand side equal to the right-hand side, but it's not a mathematical argument because that's based on guess, even though that guess is an educated one. But then you need to prove it. Then you can prove it using mathematical induction. Okay, I just want to wait, I don't know, 2 minutes is enough. Then when you give me the formula, then you need to, because this is a very, very simpler. I don't want to spend time on it. I can go on. Okay, so can you give me the formula here? Yeah, I give you 3 minutes. You can think a little bit about that. Okay, did you get the pattern?
Nope.
It's not, so let me, because I want to at least start the next part. So let me calculate, how do you find the pattern? So it means that let us take n equal to 1. Then can you tell me how many terms I need to consider when n is equal to 1? And the trick I told you, you put n equal to 1 here, it becomes 1 divided by 1 times 2. That's exactly the first term. Okay,
Papa?
so yes?
Is it n over n plus 1?
Yes, that's correct, thank you. So n equal to 1 becomes 1 over 1 over 2, yes? If n is equal to 1, the answer is 1 over 2. But might be you are making the same mistake again. What do you write for n equal to 2? Can you tell me? The people who couldn't got the pattern. So what do you write for n equal to 2?
1 over 1 times 2 plus 1 over.
Yes, exactly.
2
You need to
times
consider both of them because I told you a rule of thumb. If I put 2 here, it becomes 1 over 2 times 3. But 1 over 2 times 3 is not the first term, is the second term. But I told you, you have to keep from the first term to that term. So for n equal to 2, you have 1 over 1 times 2 plus 1 over 2 times 3. But if you calculate this, this is 1 over 2, 1 over 6. You calculate it with the common denominator 6. 3 times plus 1, it's 4 over 6. It becomes 2/3. It's not probably enough to see the pattern. Let me write n equal to 3 as well. So if I put n equal to 3 here, it becomes 1 over 3 times 4. 1 over 3 times 4 is the third term. So it means that I need to keep all of them. So it becomes 1 over 2 plus 1 over 2 over 3 plus 1 over 2 over, 3 times 4. 3 times 4. But I don't need to start from scratch because this I calculated before. It is 2 over 3. So this becomes 2 over 3. 1 over 3 times 4 is 12. And the common denominator is 12. 4 times is 8 plus 1. It's 9 over 12. And if I simplify 9 over 12, it becomes 3 over 4. And I think now the pattern is revealed, yes? When n is equal to 1, you have 1 divided by the next number 2. When n is equal to 2, you have 2 divided by the next number 3. When n is equal to 3, you have 3 divided by the next number 4. So what would be the guess? So the guess is that. So the guess, the conjecture is mathematical term. So conjecture is 1 over 1 over 2, 2 over 3 plus 3 over 4 up to 1 over n times n plus 1 is equal to n over n plus 1. Okay, I don't want to solve it for you. So if I give this thing in the exam, so you can motivate your guess, your conjecture by doing this, and then you say that now we prove this statement. Now I prove this statement by induction on n. Yes, and then that is up to you to complete this. This is a very simple example. Okay, so I don't think that I can start the new lesson. So on Monday, more or less, we will be able to finalize this chapter finally. This mathematical induction is very important. My goal is to bring different examples from different parts of mathematics. That's also, by the way, in the book. So the next topic, we will talk about how to prove inequalities, and then how we use this in proving some of the statements in number theory. That's also in the book. And then how we can use this idea to prove some geometry problems. Okay. So these are the only things left from this chapter. And the exercises in the book are quite, I would say, advanced. So let me bring the book. There is an exercise I recommend you to really work on it. So it's a very nice problem. Oh, this is math 4, so math 5. Yeah, so the exercises, yes, exercise 1245 in the book. 1245 is a very good example. So if you can solve this, because this is a little bit tricky, especially in interpreting how to write pk, how to write pk plus 1, how to write p1. It's page 35. So this is very, very interesting problem. Okay, so let me also write one problem from trigonometry for you here. So exercise, and then we are done. Okay, so we are supposed to prove this by induction on n. Prove that for all natural numbers n, we have, so let me write these two for you. So cosine x multiplied by cosine 2x multiplied by cosine 4x multiplied up to cosine 2 to power nx is equal to sine 2 to power n plus 1x divided by 2 to the power of n plus 1 sine x. Okay, so that's number 1. And number 2, I don't know if that is very simple, but if you want, you can think about it as well. Cosine alpha, cosine 3 alpha plus cosine 5 alpha. And then you continue until cosine 2n minus 1 alpha is equal to this expression, is equal to sine 2n alpha. Let me put the brackets around them, even though it's not necessary. Divided by 2 sine alpha. So if you want, you can put a pair of brackets around. Okay, so these 2 problems, I recommend you, if you are interested to improve your skills, you can work on it as well.